in this sets of problems, we will be now focusing more on code provisions on NSCP, National Structural Code of the Philippines. Okay, so I have here a soft copy. Okay, but uh, as a disclaimer, no, I also have a hard copy of this. So I bought an original hard copy of this from ASEP. I also have the latest edition, which is NSCP 2015 second printing. But in this video, I am more what do you call that? I'm more adept on using 2010 because as you see, I already bookmarked this NSCP 2010. Okay, and this is just the first printing, I guess. Okay, I suggest you just update uh, well the content here from 2015. But basically, especially on earthquake provision, there's not really much changes. No, in fact, the problems here are from a textbook in 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 a okay. So the textbook here we're using UBC 1997. But if you will notice, with the approach we have using NSCP 2010, we still came up with the same answer. Okay, so that means majority of the provision, especially on seismic provision, if you refer to UBC 1997, there's really not much changes. Okay. Okay, so for example, first problem, the natural period of a building is 4 seconds. At the roof level of the structure, the force F sub T, which is an additional to the base shear, should be determined by which of the following formulas? Okay, the solution is here. F sub T, or the additional force at the roof level, is 0.07 TV, wherein T is the period, V is the base shear. Okay, so if you have a 4-second structure, 0.07 times 4 times V, you got 0.28 V. Okay. Let me show you the exact provision of that here. So as per NSCP 208.5.5, so this one. Okay. So this is the snippet from the code 208.5.5 under vertical distribution of forces. You got here the concentrated force F sub T at the top, in addition to F sub N, shall be determined from the equation 0.07 TV. Okay. The value of this T shall be the period that corresponds with the design base shear as computed using equation 208-4, which is yung V equals CVI over RTW, that formula. Okay, also, it says here, FT need not exceed 0.25B. So, you should not exceed, no, 0.25B. And FT is 0 if your period is less than zero point 0.7 seconds. So, you can ignore F sub T if the period of structure is less than zero point 0.7. So, kumbaga, pag stiff yung structure mo, say low rise, mga 4 story is about 0.5 seconds lang eh. No? So, mga 4 story, that means wala ka ng F sub T. Okay, in general, no? Okay, because the period is 0.7 seconds or less. Okay, so let's comply this 0.25B. Let's check. Okay, so 0.28V, we got 0.28V here because 4 seconds. Masyado mataas yung period na yan, no? So 0.28V is greater than 0.25B. So as per code, you should not be greater than 0.25B. Okay, so 0.25V governs. Okay, as per NSCP 2010, 208.5.5. Please update this using 2015. Okay. Okay, next problem. A structure consists of a special moment resisting steel frame and shear wall. According to NSCP, what is the lowest percentage of base shear that the special moment resisting steel frame must resist independently? So when we say moment frame and shear wall, so if I draw that, it's something like this. You have the moment frame. When we say moment frame, it's a purely beam column or girder column resisting the earthquake. But we have when you have a shear wall, say introduce shear wall here, so buhos siya, it's no longer as a moment resisting frame or MRF. So it's now called a dual system. Okay, from the word dual, dalawa, no? Two. Okay, so there's a special requirements when you use dual system. That means two. You have dual means two. Therefore, uh, the moment frame coupled with the shear wall will resist the earthquake. Okay, so what is the lowest percentage of base shear that the moment frame must resist? So, okay, so the answer there is as per NSCP 208.4.6.4. Oops. Wait. 208.4.6.4. Is that here? Let us see the code. And this one. 0.4.6.4 dual system. Okay, what is a dual system? A structural system with the following features. An essentially complete space frame that provides support for gravity loads. And resistance to lateral load is provided by shear walls or brace frames, okay, as you observe here, and the moment resisting frame. It could be SMRF, IMRF, MMRWF. Okay, so this is the special provision. The moment resisting frame, which means the beam and column only, shall be designed to independently resist at least 25%. Okay? So dapat kasi ang tendency of this system, lahat ng base shear i-attract ni shear wall. Okay? But sabi ni code, wag kang umasa basta-basta kay shear wall, no? At least, no? At hangga't maaari 25% ng base shear madala dapat ng moment frame. Okay? Moment frame could resist at least 25%. Okay? In fact, so this is a challenge in to structural engineers because you need to tweak the software because remember when you do analysis in software, it's stiffness method. No, once you input the model, the geometry, the cross section, uh, the stiffness will be there. Okay, so how will you assure that 25% of base shear will be transferred to moment frame only? So you need to tweak something on the software. Okay, but other software can do that. I think like um, Istaad cannot do that explicitly, no. But in what software was that? RAM, no, RAM can do that already. Okay. Okay, so that's it. 25% as per NSCP 2028.4.6.4. Okay. Okay, next problem. Consider an 80 feet or 24.4 meter special moment resisting frame. Applying method A of, well, let's just replace this with NSCP. Okay. As you notice, no, this textbook is from an American textbook, but NSCP is still applicable because we're just following UBC 1997. Okay, and CBC is actually this is California Building Code. Now, remember, California is a seismic state, no, a seismic region, no, California Building Code, and most of our seismic code, which is printed in UBC 97 came from California Building Code, which we adopt later on. Okay, so 24.4 meters special moment frame. What is the period of the building using method A? Okay, so as per NSCP 208.5.2.2, this is the formula. This is actually the method A. T equals CTH raised to 3/4. Okay, and then remember your frame is special moment steel frame. Okay, so let's see 208.5.2.2. Okay, there's that 208.5. Okay, okay, so here 208.5.2.2 structure period method A. So this is the formula T equals CTH raised to 3/4, where C sub T is 0.0853 for steel moment resisting frame. Okay, so using that value, we will use that in our problem. 0.0853, wait, here. So CTH raised to 3/4. Yeah. So 0.0853 times 24.4 raised to 3/4. Okay. So you get 0.94 seconds. Okay. So next problem. So there are three types of structures are shown. They are located at a site in seismic zone 4, say Manila, and underlain by the same soil profile. If an earthquake occurs with a predominant period of zero point 0.6 seconds, okay, so imagine the ground acceleration, which you did your first assignment. There's a ground acceleration, and that the period of that uh, wave, seismic wave, is zero point 0.6 seconds. So the tendency of your structure, if you also have the same period, you will experience resonance. Okay, so when you experience resonance, the displacement will be much higher. Okay, so which of the following building has the greatest possibility of being in resonance with the earthquake? Because so we have three structures. Then if period is given as zero point 0.6 seconds, so let's find out the period of these three structures. So using the same formula we did earlier, wherein T equals CTH raised to 3/4. So plug in the formula here. But take note that three structures has different um, framing system. The type 1, the first structure is concrete shear wall. Second structure is special steel moment resisting frame, the same as the previous problem. So therefore your CT is 0.0853. Okay. Next, last structure is RC frame. So what's the CT of that? So let's see. So concrete shear wall and RC. What's the CT of concrete shear wall and RC? There's that here. Okay. So we already know for steel moment, it's 0.0853. So here for RC, it's 0.0731. So how about the concrete shear wall? So nothing here, but except that 0.0488 for all other buildings. So we can use 0.0488. Okay. Okay, where's the problem? Here. Okay, for concrete shear wall, 0.0488 multiplied by the height, which is, as you see, it's 28.4, it's the highest, raised to 3/4, you got zero point 0.6 seconds. Okay, for structure 2, since it's special steel moment frame, it's 0.0853 times 13.5 raised to 3/4, zero point 0.6 seconds also. Okay, and the last is 0.0731 because it's RC, okay, reinforced concrete moment frame. The height is 16.6 raised to 3/4. It's also zero point 0.6 seconds. Okay, so you observe that although they have different um, height, you generally have the same period because the framing system is different. Here we have concrete shear wall. Okay, so it's high, but it has shear wall, so it makes the building stiff. Okay, while this one, second structure, is low, but you're using steel, so such that the period of these two is almost is equal. In fact, while for the third structure, yeah, it's RC, but it's higher than the structure 2. Okay, so in short, we have the same, in general, we have the same period of these three structures, and if the dominant period of the earthquake is zero point 0.6, so expect that you can experience resonance on all these three structures. Okay, so next is so we have a hypothetical problem here. Say a 10-story office building underlain with soil profile type SB in, say, Makati. Your R is 5.6. 5.6 is hypothetical. I indicate hypothetical because I think in our NSCP, you cannot really get an R of 5.6 um, typically. Okay. So the weight of the building is 2,000 kips, or 907,185 kilogram. So NA in NB is 1. Okay. What is the maximum allowable design base shear for the structure? So maximum. Okay. Allowable design base shear. Minimum, sorry, minimum. Minimum allowable. But as per NSCP 208.5.2, our minimum is this two. 0.11 CAIW and zero point 0.8 Z NVIW over R. So let's see 0.11 and zero point 0.8. Where's the formula? I already got the snippet of that here. So these are the four formulas of base shear. So the minimum is are this 0.11 and zero point 0.8 Z NVIW over R. 0.11 CAIW. Okay, so let's use that. Okay, where's that? So plug in the value. Okay, 0.11, what is our CA? How do we get CA? Remember, the soil type is already given, SB, okay? And NV is given, or NA is given here, 1. So SB and our NA is 1, so zero point 0.4 times 1, okay? So here, 0.11, CA is zero point 0.4, because zero point 0.4 times 1 is 0.4. And then importance factor is only 1 because it's a office building, or an office building has an importance factor of 1. Okay, and then the W, okay, 907,185 kilogram. Then multiply that by 9.81 to convert as weight. So I got 391.5 kilonewton. How about the next formula? 0.8 Z NVIW over R. So zero point 0.8 Z is zero point 0.4 because you're in Makati. Okay. So seismic zone 4 is zero point 0.4, Z is zero point 0.4. And then NV, what is our NV? Given is 1. So that's it, 1. I is 1. Okay. And then R is 5.6 given. Okay. Then the W is 907,185 multiplied by 9.81. So you got 508.5. So what governs is 391.5 kilonewton. Okay, why? So because it's lesser than zero point 0.8 ZNV. What does the code says about that? Yan. Okay, the total design base shear shall not be less than the following. In addition, the total base shear shall not be less than the following. Okay, so 391. Yeah, okay. It shall not be less than 0.11 CAIW. So, okay. Let's see. Okay, so we have there's a 5.6 here, but ordinary moment frame only. Uh, but if you notice under zone 4, it's not allowed, not permitted. Okay, so that's why I wrote down hypothetical. Okay, just for discussion purpose. Zone 4. Okay. Again, as I said, no, typically your R should be 8.5. Okay. So next problem. So a building must be designed that will not require any additional force at the roof, wherein Ft equals 0. Okay. So assume the maximum possible natural period for this building. So use R equals 5.5. So again, hypothetical. Soil type A, okay, and Z equals zero point 0.4, and near source factor NV equals 1.2. What is the design base shear using NSCP, of course? So if we use Ft equals 0, okay, lay down the parameters here. Remember, using NSCP, this is the base shear, right? V equals CVIW over RT. So plug in all the available parameters. So what's our CV? So later, I is uh, typically 1. So, okay. R is 5.5. Uh, Period is zero point 0.7. Why zero point 0.7? Because it says here that Ft equals 0. Remember the provision earlier? If your period is zero point 0.7 seconds or less, your Ft is 0. Okay, so that's why we use zero point 0.7. So how about CV? How do we get CV here? Okay, where is CV? Let's refer to the table here. Here. So this is the value for CV. We got 0.32. Why do we use 0.32? Because your soil type is A here. Okay, this one. Okay, shower table here. So because our soil type is A, and then your CV is 0.32 because we're under zone 4. Okay, so CV is 0.32 NV. Okay, so what's our NV is 1.2. So plug in 0.32 times 1.2 times 1 over 5.1.7W. So we got 0.10 IW. Okay, so that's letter B. Okay, next. Maybe let's first this. No computation needed. So an engineering firm is designing a hospital in seismic zone 4. Okay. The building has a vertical geometric irregularity. The height of the building is 65 feet or 19.8 meter. Which type of lateral force procedure should be used? Okay, is it A, static, B, dynamic, C, either static or dynamic, or neither? So according to the code, when shall we use the dynamic? Have here the... Okay, so as per the code, so this is the definition. We can use static, okay, under 4 conditions. Number 1, you can use static if if you're regular or irregular, no? If you're in seismic zone 2, so that means say in Palawan or Sulu Tawi-Tawi, because since you don't necessarily expect much earthquake there, that's why you can use a simple static analysis. Okay. Number two, regular structures under 75 meters in height. So say box type structure, the the framings are symmetrical, okay? So static can be okay. Number three, you can also use static if you're irregular structure, but if you're not more than 5-story, okay? And then number four, structures having a flexible upper portion supported on a rigid tower. So it's a long definition. How about in dynamic? So in dynamic, therefore, as per number three, if you're irregular but more than 5-story, you will use dynamic, according to the definition of static, right? Okay. But our problem is what? How many story is our problem? Okay. The height of the building is only 19 meters. So it's a low-rise building. Although it has a vertical geometric irregularity. So, but it's generally low-rise. Okay. Okay. Most likely, if we assume a 4 meters per story, so it's just 5-story. You can qualify this as 5-story, right? 4 times 5 is 5-story. Although 4 meters is quite high. Okay. How about the definition of dynamic? So definition of dynamic, okay. Structure 75-meter or more in height, so high rise, okay. Mid-rise to high rise. And then structures having stiffness, weight, or geometric irregularity, okay. And of course, to supplement this, so if your structures is over 5 stories or more, and then zone 4, so you will be using dynamic, okay. So there's really a gray area there. So in short, if you refer to the code, uh, you can use either static or dynamic. But personally, with the availability of softwares, of computers, uh, I would suggest you use both static or dynamic. Okay, because in dynamic analysis, you will capture the more realistic behavior of your structure. Okay? And also, if you use dynamic, you will be required by the code to analyze also using static because there will be a scaling later on because you need to compare the base shear from dynamic and static analysis and then scale that up in case dynamic analysis produce a lower base shear. But in dynamic, again, the behavior or the distribution of forces is more realistic because you consider the irregularities. Okay, we have a project also. It's just 2-story with mezzanine. We also use dynamic. So because once you have irregularities, you need to capture the behavior. Okay, so next problem. A structure in seismic zone 4 has an R value of 8.5. Zone 4, 8.5. Remember, I told you the default R is almost always 8.5 in zone 4. So what may be the maximum design height of this structure? Okay, so let's refer to our code here. Zone 4. Okay. So if your R is 8.5, okay, under zone 4, so let's see, 8.5. So what do you notice? It's NL. So no limit. So 8.5 again, NL. So no limit. Okay. So in short, in theory, no, you can use uh, R equals 8.5 in zone 4 with no height limitation. Okay. I think so. This will be the last problem for now. That. So an 80 meter, sorry, a 24.4 meter a special moment steel frame, 8-story, has a fundamental period of 0.7 seconds. So per the NSCP, okay, I'll use this. Per NSCP, what is the maximum allowed design level response displacement or the total story drift? Okay. So as per NSCP 208.5.9.2, the formula for delta M is zero point 0.7 R delta S. I'll show you the code provision. Where's that? So the answer is again no limit, right? The answer here is no limit. Where's that code provision for 0.7? Ah, here. So determination of delta M. What is delta M? The maximum inelastic response displacement. Okay, so this is consistent with what I'm saying before, right? So I've told you that, say we have a response spectra. This is elastic, okay? Response spectra is acceleration versus period. But the code, what the code did is we reduced this response spectra for inelastic response, okay? This reduction is made by introducing R. Remember, V equals CVI over RTW because R is in the denominator. Now, in short, the code uh, wants our structure to behave inelastically by introducing R. Now, the consequence of that is you are now using a reduced base shear, right? Because it's a lower acceleration, reduced base shear. Okay. Once you use a reduced base shear, therefore, your cross section will be smaller. Once your cross section gets smaller, what will happen? Your displacement will tend to increase because you're getting flexible. Okay. Your structure is becoming flexible, right? So, so in order for the code to counter that, match this displacement or drift, so it introduces this formula, delta M is zero point 0.7 R delta S. Notice that in the formula, you have still the R, because the code reduce the base shear by R by introducing R, but in terms of the maximum displacement, it introduce again the R. So it magnifies your displacement. Okay, so zero point 0.7 R delta S. What is delta S? Delta S is deformation. What's that? Where is delta S? Anyway, that is the here. Design level response displacement. Okay. And also, as per NSCP 208.5.10.1, 5.9.2, this is 5.9.2. How about 10.1? This is 208.5.10.1. What does it says here? Delta M, okay, shall not exceed 0.025 times the story height for structures having a fundamental period of less than zero point 0.7 seconds. Otherwise, it's zero point 0.02. So it's either 0.025 or 0.02. Okay, so that's why, so 10.1. Okay, so since our period is zero point 0.7 seconds, you will be using 0.02. Okay, so plug in that 0.02 times height. What is our height? 24.4. Okay, so why do we divide by 8? Because the building is 8-story. Remember, the drift is actually the difference, no, or the ratio. Say you have this structure. So this is your total drift, total displacement, the drift is obtained by getting delta, say, x1. This is delta x2. So the drift there is delta x1 minus delta x2 all over the height, the typical height per floor. Okay, that's why we need to divide by 8 in order to get the height per floor. Okay, so 24.4, which is the total height, divide by 8 to get the height per floor. Then multiply by 1000 to convert in millimeter. So I got 61 mm, the delta M, okay, using 0.02H. Then remember, plug in 0.7 R delta S, 0.7, 8.5 delta S, then substitute 61 mm here. I got delta S as 10 mm. So that is your design level response displacement. Okay, now when you consider the inelastic lateral displacement, you will multiply that by R, which is 8.5, which is, and then zero point 0.7, you will get the 61 mm inelastic displacement. While this one is just the design level response displacement. Okay, so that's the allowed design level displacement. So it's sort of saying that in your model, uh, you will be getting 10 mm. But considering the inelastic response of the structure, you can experience up to 61 mm. So, as, so that's the idea. Okay. So that's it for now. So we'll be solving another problem on the next uh, video.